Okay, last time we were talking about charging, discharging, or at least placing a charge on neutral matter, or previously neutral matter. And we did some playing around with some sticky tape, and you'll be doing some more playing with sticky tape in the lab this week. And we discussed polarization. Okay, so polarization being a separation of charge. And we talked about the mechanism by which, or this is the mechanism by which, a piece of charged matter is attracted to neutral matter. So we saw the tape attracted to my hand, for example. And we talked about induced dipoles. Where if you have a neutral atom with a positively charged nucleus and a negatively charged electron cloud surrounding the nucleus, and if you apply an electric field, so if you bring a positive charged object or a negatively charged object nearby, it's going to apply an electric field. So if we have an electric field applied here, I'll just call it E applied, which could be due to, for example, some positive charge over here or some negative charge over here, what have you, then it causes a shift in the electron cloud, right? The electron cloud is lightweight compared to the nucleus. It's negatively charged, and so there's going to be a force on it due to that applied electric field. The force will be that way because of F equal to QE. The force is going to be in the opposite direction if we're talking about the electron charge being negative. And it shifts a little bit, and it reaches equilibrium when the attraction due to the positively charged proton is balanced by this new force due to the applied electric field. And so what we see is something in the end that looks more like this, although this is a pretty gross exaggeration of what actually happens. But you have a separation of charge, a higher density of negative charge on one end versus on the other end. And so this is called an induced dipole. Okay? A neutral molecule or atom becomes a dipole in the presence of an applied electric field. You had a short homework problem that was due today that just quantified this a little bit more. We talked last time about the dipole, or when we were dealing with dipoles, we talked about this quantity called dipole moment, electric dipole moment, which is given the symbol P. It's Q times S, where Q is the magnitude of the charge on either end. Okay, so in this case, it's negative E, or E, little e, for example. And S is the separation, the amount of distance that the two ends are separated. So that dipole moment here, the strength of the dipole in ordinary matter or usual insulators can be parameterized with this quantity called alpha. This is the atomic polarizability. It's just telling you the extent to which a neutral atom becomes a dipole when there's an electric field applied to it. So you can think of this as the applied electric field due to some other external charge acting at the presence of some atom, and it creates a dipole moment. It causes it to polarize. And it's a property of the material. It's a property of matter. Okay, so for example, carbon atoms, a carbon atom has a particular atomic polarizability of something like 10 to the minus 40, and the units are coulomb meters over newtons per coulomb. It's just, again, it's just a parameter or a property of the material, and the larger the atomic polarizability, the more it's going to polarize, the bigger the dipole moment's going to be when you apply the same electric field. This is a pretty tiny number, but when you have lots and lots and lots of atoms in a material, then it adds up. Okay, so you get to see large effects. We can see the tape being attracted to my hand, even though the individual molecules may be polarizing only a tiny, tiny bit. Okay, so you had a brief question on that. So these tape experiments, these that we did last week and you'll be doing in lab this week, kind of simple things to play around with just to get an idea of charging, discharging, polarization, that sort of thing. But they do raise some interesting questions that you should keep in mind as we're going through this chapter. The first one we've already talked about, which is why does a charged object attract neutral matter? Okay. So we talked about that last time. Essentially, if we have this positive charge here that is creating a dipole moment, then we can think about the dipole itself, this induced dipole, and let me now draw it in this schematic form that we're going to use. Here's our positive charge. Here's the induced dipole, which is now negative on one end and positive on the other. Well, the dipole itself is going to create an electric field at the location of the original charge. So the electric field due to the dipole, if we're closer to the negative end, is going to be pointing that way. And then the field acting on a positive charge is going to produce a force in this direction, same direction as the electric field. So it's an attractive force. If we had a negative charge brought near a neutral molecule, it would polarize the opposite way, right? Because the negative charge would tend to repel the electron cloud in the molecule. We get an electric field due to the dipole now that's pointing in this direction. But because we're saying F is equal to Q times E, and Q is now negative, the force is going to be in the opposite direction. Okay, so we get an attraction, and then just from Newton's third law, if you have the force due to the dipole on the charge being pointing in that direction, then the force on the charge due to the dipole would have to be equal in magnitude and in the opposite direction, right? So we get an attraction no matter what case we have. The polarization always occurs such that we get an attraction. We just can't get a repulsion between neutral matter and a charged object. Okay. So that one's taken care of. Other things that we can think about